Hi everyone, so let's continue our conversation on chemical equilibria, and we're looking at some general questions on chemical equilibria. So the example that we are going to look at is an interesting example. It's actually a reaction that's important, or it says important for smog formation, but what it means is it's a reaction that takes place when smog is formed. And it says when ozone reacts with nitrous oxide, it forms oxygen gas and nitrogen dioxide. It has a very large Kc value, and it also has a negative enthalpy of reaction, meaning it's an exothermic reaction. And we'll see why that information is quite important. We're then asked to answer the following questions for this reaction. So it says an initial mixture of ozone, nitrous oxide, nitrogen dioxide, and oxygen is prepared and sealed in a container. We're then asked to calculate the concentrations of each species at equilibrium. So this is a classic equilibrium question. We're given specific initial concentrations of each of the four gases that participate in the equilibrium, and we're told these are the initial concentrations. What are the concentrations at equilibrium? Right. So the first important thing is to determine is whether or not this reaction isn't maybe accidentally already at equilibrium. So let's go ahead and calculate Q. All right, so Q is of course O2, so it's a product multiplied by NO2, which is also a product, divided by the reactant concentrations, ozone, nitrous oxide. Alright, and then these concentrations that we are given. So oxygen is 8.2 multiplied by 10 to the minus 3. Nitrous oxide is 1.0 times 10 to the negative 5. Times 10 to the negative 6. And nitrous oxide NO2. No, sorry, that's just a writing mistake. This should be NO2, so that's 2.5 times 10 to the negative 4. And then this is 1.0 times 10 to the negative 5. Right, yes. 8, 2.5, 1.0, 1.0 times 10 to the negative 5. Yes. Okay. And this gives a value of a lot. So 205,000. So 205,000. So if we look at that and compare it to the Kc, we still see that Kc is still a mammoth way away, because Kc is 6.0 times 10 to the 34. So even though this is a big number, Q is a big number, Kc is still quite large. So this Q is still less than K. So Q is still less than Kc. So that means the forward reaction favored. And more importantly, we are not at equilibrium, right? Because Q wasn't equal to K. So that's what we established. We established this mixture is not at equilibrium because Q is not equal to K, and that the forward reaction is going to be favored until we reach equilibrium for this mixture of gases. So to determine the equilibrium concentrations, we need to, or we're going to use the ice table method. So I've already gone ahead and written down our ice table method. So we know we start with the initial concentrations. We know the Q is less than K, so that infers to us how the change in concentration is going to be affected. Right? So that means that our reactant concentrations must decrease and our product concentrations must increase, right? And everything must increase by X amount, and stoichiometrically by x amount. The reaction is 1 to 1 to 1, so that means everything must decrease by x or either increase by an x amount. Alright, so therefore at equilibrium, the ozone is this minus x 1 times 10 to the negative 5 minus x. Oxygen gas is 8.2 times 10 to the negative 3 plus x, and nitrogen dioxide is 2.5 times 10 to the negative 4 plus x. Alright, so then to determine x we can use Kc. I've already done that, so I've just written down Kc is equal to that big number and equal to that expression. So now that we have the equilibrium concentrations with x, we can go ahead and substitute in those. So O2 is 8.2 times 10 to the negative 3 plus x. NO2 is 2.5 times 10 to the negative 4 plus x. And ozone is 1.0 times 10 to the negative 6 minus x, and nitrous oxide is 1.0 times 10 to the negative 5 minus x. Alright, important test. Can we do the approximation? I hope it should be obvious that Kc is a very big number and none of our initial concentrations even come close to that Kc number. So an approximation is not valid here. So what we should do is we should expand the numerator and the denominator. And what I got is 2.05 for the numerator times 10 to the negative 6 plus 8.45 times 10 to the negative 3x plus x squared. And at the bottom I got 1.0 times 10 to the 11. These numbers look much worse than they actually are. So once you start working with them, then they become actually kind of okay. Plus x squared. Alright, and we can remember that we can just bring that down. That's equal to 6 times 10 to the power 34. You will see now that I'm going to make a small approximation somewhere, but that's just because it's not going to have an effect. Alright, so now let's multiply our denominator to the left. So for example, okay, so let's just multiply that now to the left. So 1.0 times 10 to the negative 11 times 6 times 10 to the 34 becomes 6.0 times 10 to the power 23, and so on. So then I get 6.6 times 10 to the power 29x plus 6.0 times 10 to the 34x squared is equal to 2.05 times 10 to the negative 6 plus 8.45 times 10 to the negative 3x plus x squared. So now let's put everything together on one side. I'll group the terms. So we have 6.0 times 10 to the power 34 minus 1 x squared. And we also have then minus, so that will work, minus 6.6 times 10 to the power 29. That will then become a plus 8.45 times 10 to the minus 3x. And the last one, which is also kind of a joke, is then plus 6.0 times 10 to the power 23 plus 2.05 times 10 to the power minus 6 is equal to 0. Alright. Now, hopefully, what I want you to realize is that this bracket, and this sum here, we can even put it in a bracket of its own, are equal to the big number. So meaning 6 times 10 to the power 34 minus 1 is equal to 6 times 10 to the power 34. Because 6 times 10 to the power 34 is a massive number. I don't care that you're subtracting 1 from it. You can even put it into your calculator. Your calculator is just going to give you 6 times 10 to the power 34. So I'm quite sure it's just going to give you 6 times 10 to the power 34. Because it doesn't matter. You're going to have to subtract something of the same magnitude from it, and 1 is not nearly of the same magnitude. So that's going to be what that bracket gives us. This next bracket, you can see you have 6 times 6 times 10 to the power 29 plus 8.45 times 10 to the negative 3. That's 0.00845. That little bit, that 8.00845 contributes to this sum is not significant. So we can approximate, or I'm not going to, it's not even an approximation, it's just this sum is equal to 6.6 times 10 to the 29. So again, you can put it into your calculator, but it's going to give you, I'm quite sure it's going to give you this value. And the final part, again, you have 6 times 10 to the power 23 plus 0.000000205. That's not significant. Those numbers aren't significant, so you just have to take the big number. 0 times 10 to the power 23 is equal to 0. So now we have a normal quadratic expression, right? Let's see, I might need an extra page here. So now we have a normal quadratic expression. So how do we solve quadratic expressions? Well, we use the quadratic formula. So that means x is equal to minus b plus minus square root of b squared minus 4ac divided by 2a. Alright? And if you put in your a, so a, that looks like a 9, a, b, and c, put in those values, then you get x1 is equal to plus 1.0 times 10 to the negative 5, and I got x2 equals to 1.0 times 10 to the negative 6. Each of these are molar quantities. So let's now check which one of those are possible. And I mean, initially it seems like both of them are possible, but if we look at, for example, the equilibrium value, or equilibrium concentration of, the equilibrium concentration of ozone, then notice that if the value is x1, 10 to the power negative 5, you will get a negative concentration for the equilibrium concentration of ozone. So that means this is an impossible value or an impossible solution. Alright, so that means we go with x2. Alright, so that means our equilibrium concentrations are as follows. The equilibrium concentration for ozone is equal to 1.0 times 10 to the power negative 6 minus x. X is 10 to the 1.0 times 10 to the negative 6. So that means ozone rounded equals to 0 molar. That's why ozone doesn't exist. Well, doesn't exist or isn't available in the atmosphere. Alright. Nitrous oxide at equilibrium is equal to 1.0 times 10 to the negative 5, also minus x, and this is rounded to 9.0 times 10 to the negative 6. We can also calculate the concentration of O2 at equilibrium. Alright, that is just, it is equal to 8.2 times 10 to the negative 3 plus x. So it rounded was 8.20 times 10 to the negative 3, right, which in principle is just two significant figures remains 8.2 times 10 to the negative 3, and then the last one, NO2 at equilibrium was equal to 2.5 times 10 to the negative 4 plus x, rounded, you're going to see, will give you 2.51, some numbers, times 10 to the negative 4, but then rounded to two significant figures gives you 2.5. And the only interesting thing about that is that you can see, well, your reactant concentrations decrease to almost about 0. Well, I mean, the one definitely decreases to basically about 0. This is very close to almost 0. And your product concentrations are, I mean, barely increased because they were already much larger than the reactant concentrations. But it's just interesting for you to note that. But I wanted you to work with some big numbers and see some interesting things. All right, so that was the first part of the question. Right, now, B part of the question. If the temperature is increased, as on a very warm day, will the concentrations of the products increase or decrease? All right. And as usual, so how we need to judge that is we need to think of it in terms of the enthalpy. So the enthalpy here is negative, right? So the enthalpy is negative, and that implies it's an exothermic reaction, and that means we can actually write the heat as a product. So for this reaction, we can actually write it as in equilibrium with O2 gas plus NO2 gas plus heat, right? Because it's exothermic, it means heat is being given off. The question says, if the temperature is increased, will the concentration of the products increase or decrease, right? So what are we doing? We are increasing the temperature. That means we are adding heat. If we are adding heat, which side of the equilibrium are we increasing? Well, we are increasing the product side. We are increasing product side of equilibrium. Or rather than using increasing, we must say we disturb the product side of the equilibrium, right? So if we disturb the product side of the equilibrium, what does the system want to do? How will the system respond? Well, the system will respond in the opposite manner. So hence, the system will respond by decreasing the product concentrations and hence increasing reactant concentration. Or differently put, right? So it's going to increase the reactant concentration, decreasing the product concentration, hence shifting the equilibrium to the left. The question specifically asks for, will the concentration of the products increase or decrease? The products will decrease. Product concentrations will decrease. All right? And that's why smog dissipates when the heat rises. Okay, interesting. Just to note. All right. I hope this gave you some insights further. Once again, same old. And I'll see you in the next video.